Let's talk about evaluation strategies. Here on the left, we've got an arithmetic expression. If we run this in Shplait, we have to evaluate in a specific order. So Shplait has an evaluation strategy that's built into it, and that's the one that we're going to need to follow if we run this code through Shplait. This term also makes sense as an algebra expression. And if we're working in algebra, then there's many different orders that we could take for evaluating the expression, as long as we follow order of operations. For example, we could do the multiplication first to get 12, and then the subtraction, and then add the two together. Or we could do the multiplication second. First do the subtraction, then multiply and add. In algebra, we're free to take either order, and this freedom means that we can skip work in some cases. So if we're working in algebra, and we see that there's a function f that just returns its first argument, and we have some function g, which maybe has a big definition on the inside. And then we see a call to f, giving 17 as the first argument, and then a huge pile of g's applied to 18. In algebra, we can substitute straight away to 17. We don't need to evaluate the result of all those g calls because we know, looking at the term, that those g's are not going to be used. If we're working in Shplait, on the other hand, we have to evaluate both arguments to the function before we can see that the result is 17. That's great, but what does this have to do with actual programming? Well, there are lots of ways that you can wind up doing unnecessary work in a program. For example, when building these slides, we have functions on the inside that do something like layout text. So take in a big string, txt, and then take a width and a height that that text should fit into. So then this function will do some work to flow those lines into a paragraph and then finally draw a picture. So we can use layout text, for example, to make a picture of Lincoln's speech. Starts off with 4 and then it has to fit in the width 800 and the height 600. At this point, we have a picture object, but we don't always use the resultant picture. It could be that we pass that picture into a function that asks for only the width. And then at this point, we don't need to do any of the work to lay out the text. All we need for the result here is that number 800 that we passed in as the width. So there's unnecessary work if this is our entire program. Here's another example. We've got a function that reads all characters of a file. And what we want to do down at the bottom is make sure that that file starts off with a #line. So we're looking to see if the first element of the content is equal to a hash. If it is, then we go on and process the file using some other function. And if it's not, we raise an error immediately. The way this code is organized, we do a lot more work than we need to end up in this error case. So suppose the file does not start off with #. What we wind up doing is reading all the characters of the open file, then checking the first one and then giving an error. We didn't need to read anything past the first character, but we wound up doing it anyway. So this is another example of unnecessary work. We could reorganize the code to avoid doing that unnecessary work, but it's going to take a lot of reorganization to get there. All these examples of unnecessary work are meant to motivate another choice in the language design space. So far, the languages that we've used have been eager, but the other option is for the language to be lazy and only compute what's needed to get the final result of a program. So in a lazy language, we can write the code exactly as we have here for processing a file, but it's only going to get the first piece of content. So our lazy language would not read all of the characters. It would stop short of doing all that work and just do what's asked for to get to the if case and then execute the error right afterwards. One very interesting thing that you can do in a lazy language, which you can't do in an eager language, is specify an infinite amount of work and still have the computation finish in a finite amount of time. So here we have a function numbers from, which in an eager language would loop forever. So it takes in the number n and then creates a cons pair with n at the front and then numbers from add 1 of n. In a lazy language, that's just fine. And now we have a list, non-negative, which is going to be built up lazily whenever it is that we need it. So if we ask for an element somewhere along the list, then at that point, our lazy language would do the work of constructing the first elements of that list, but then it will stop and it won't go on for off into infinity. To sum up, most languages are what's called eager programming languages, and examples include Shplait, Java, and C. These languages all specify an evaluation order, and so they reduce expressions down to a value whenever they encounter those expressions along the evaluation path. The alternative design is lazy languages, and these avoid unnecessary work by evaluating expressions only when their result is needed. A lazy language also has an order of evaluation, but it will delay reducing the expression to a value until that value is really needed by some other expression in the program. And now in the rest of these videos, we're going to turn Mo into a lazy language to see exactly how this works.